So we've basically learned everything there is about curve sketching using calculus. We do our preliminaries. So our preliminaries are looking if we can find x-intercepts and y-intercepts, looking if there's any asymptotes. Y-intercept is always the easiest because you can plug in 0 for x. And in this case, we get 0 for y. So there's our y-intercepts. Sometimes we can find our x-intercepts, sometimes we can't. So it's a matter of factoring. In this case, I can factor out an x squared. So if I put y equal to 0, I would get x squared times x squared minus 2. And then I get x equals 0, which doesn't really help me because it was already the y-intercept. But I can solve this as well. Because if you make that equal to 0, you can move the 2 over to the other side, and you could square root both sides. It's not a pretty number, like a whole number or something like that, but it's still something that we can solve. So we know that our x-intercepts are 0, 0, root 2, comma 0, and negative root 2, comma 0. So preliminaries, we've already got 3 points that are going to help us with our graph. But now we can go through the steps of the calculus part. Our first derivative, we'll draw that number line for the first derivative, and it will tell where our graph is increasing and decreasing. And then we can use the first derivative test to find out if those points are maximums or minimums. So we'll start with that. So preliminaries in blue. Then, step 1, or the first stage, and I'll look at my notation as f of x. So f prime of x will be 4x cubed minus 4x. Set that equal to 0, and we can factor out a 4x. We can factor this completely with the difference of squares. And those are going to be our stationary points, right? Where our derivative is equal to 0 will be our stationary points. These are also critical points, but we don't have any non-permissible values we have to add to this list. So I'm going to keep saying non-permissible value stuff in questions that don't have them, just as a reminder, because it will be the first thing that you forget as soon as we get one with a non-permissible value. So now we have those values. I would check in my factored form right here. It's going to be the easiest because you can plug a number in less than -1. This is going to be negative, this is going to be negative, this is going to be negative. Don't even have to do the mental math as far as figuring out the values. And a negative times a negative times a negative will make this section negative. It's going to be decreasing. Okay? In between -1 and 0, like -0.5, negative, this one is now positive, this one's still negative, that section's positive. Between 0 and 1, 0.5, this is positive, positive, this one's still negative. And if you plug in something bigger than 1, all of those will be positive. Okay. So we get this shape. Now, as far as thinking back to grade 12, you had to graph x to the 4 graphs in grade 12. And just a reminder that if it's an even power, it will end up like a parabola. So you know how an x squared graph from grade 11, that goes like this. A negative x squared graph goes like that. So anytime we have an even power, an x to the 4, an x to the 6 graph. Oh yeah, do you want to look at some of those? Anytime that we have the highest power being even, the highest degree being even, it's going to follow this. And because we have a positive x to the 4 graph, our end behavior is going to end up like this. So when we go to our diagram, right, it's kind of telling us it's going to look like a W. We can see that end behavior looking like that as well. So just a connection between something you did in grade 12 to something that you're doing right now, or something you're going to do in grade 12, and something you're doing right now. This is what we have at this point. So we will know that -1 comma something is going to be a minimum. 0 comma 0, we already knew that point is going to be a local maximum. And 1 comma something is going to be a minimum. Right? And if this was a test that said prove that this is a minimum, you would have to show the two things, right? You would have to explicitly say the derivative is equal to 0 and show, okay, the minimum, it's decreasing, then increasing, and so on. So just a reminder of that. To find these coordinates, we would have to go back to our original equation, plug in -1, it'll be 1 minus 2, -1, plug in 1 will also be 1 minus 2, -1, to find those points. Next, I'm going to switch to purple. My second derivative. To find our inflection points, we're going to use our second derivative. We'll get 12x squared minus 4. Set that equal to 0. Move the 4 over, divide by 12, so we get 1/3 equals x squared, and x would equal plus or minus . Plus or minus √3/3. Again, now we make our number line for our second derivative. We would put minus √3/3 and positive √3/3 on there. Plugging in values to check. Since we don't have a factored form here, we'd actually have to plug in values. I hope that 0 would be an easy one to see, first of all, that this section in between negative √3/3 and √3/3 would have to be negative. Plugging in something less than negative √3/3, you can still make your mental math fairly easy. Choose -100. And you're like, well, that's a big number. How does that make my mental math easy? Well, if I plug in -100 for x, and x is squared, it's going to be a large number. Then it gets multiplied by 12. That's 12 times larger than the large number. That's larger. And then you minus 4, and you're like, okay, I'm just going to practice. I'm going to take a very big number. I'm going to subtract 4, and I'm going to see if it's positive or negative. It's going to be positive. So we can know that this section is positive, and similarly, this section will be positive as well. So we know that, and this is why this question was listed as calculator, negative √3/3 comma something will be an inflection point. Still haven't come up with a good abbreviation for that. And √3/3 comma something, I think I need the L. Doesn't seem like it's abbreviated well if it doesn't have the inf with the L seems more like inflection. And to find those values, chances are we have to plug that back into our original equation. So I scroll up to the beginning, I would have to plug in √3/3 into that original equation and figure it out. Yeah, and that is not necessarily the easiest mental math. I've got like -1/9. 5/9. Okay, that was close. So this will be, and it'll be 5/9 for both of them. And now we have a lot of stuff. If we zoom out and see what we've done so far. Right? We did the blue first, our preliminary. Then we went into the green, which is all of our stuff on our first derivative. Our first derivative found our mins and our maximums. And then we went to our second derivative in purple, and that found our inflection points. If we start to draw, and it looks like I've got some space right here. And looking at the scale of the things that I have to put on, they're not too bad. I'm going to need to plug in 0, 0, -1, -1, -1, -1, that's not -1. There we go. -1, -1, 1, -1. Those are my green points. From my preliminaries in blue, I would also have √2 and -√2, √2, 0 and -√2, 0. I have those points. And I have inflection points at -√3/3, 5/9. I'll draw those in purple. Did you get +5/9 or -5/9? -5/9? Okay. There we go. Because that was like. So there's our points. And then as far as drawing our final graph, I would start from my inflection point. So I'm going to start from a purple point, and to the left of the purple point has to be concave up. That makes this part all have to curve like this. In between, this part is concave down, and then concave up again. And we get our graph. Now I want to show you some stuff because you're going to have a lot of graphing that you're doing, and you either have a graphing calculator or probably even better is Desmos for checking. So I want to show you some stuff on Desmos right now. Is everybody done copying down what they need? Sorry, the graph is really small in the end when I'm zoomed in. But going to Desmos, you can go to Desmos and you can type in y equals x. You have to use the little hat button to go up for a power, x to the 4 minus 2x squared. And there's our graph. So a couple of things that show up nicely on the graph already is, and you can just go and click on them, it has our x-intercepts, y-intercepts, maximums, and mins already labeled. You'd have to check on your calculator, is square root of 2 1.414? It is. Okay. Notice that your inflection points, though they're not labeled. There's probably something I haven't found yet that you just type in inflection point here and it figures it out for you. But what's really cool on Desmos is if you want to, I'm going to retype this as f of x. It's just different notation. But then I can go y equals f prime of x, and it graphs the derivative right away, which is kind of cool. And now I can find my max and my min of my derivative are labeled right there. Okay? So that's pretty cool. Other things you could do, if you wanted to actually label your inflection points now, I know that this max is at negative 577. That doesn't quite match with 5/9. Oh wait, we better check. We could check our. And you can also do second derivative. 45 seconds. So you can graph all of these things on Desmos. It's kind of nice. If you want, you can just click on the graph to hide ones or just point other ones. I'm now going to look back at our equation because that 0.577, unless is not, that is equal to square root 3 over 3. Okay, so that's, oh yeah, that's the x coordinate. We're looking at the y coordinate. No, that's all good. Okay, so now I want to just check on Desmos here something. I wonder if I type in, I'm trying to, here, I can go x equals square root 3 divided by 3. That'll draw, oh, I don't want brackets. That'll draw this horizontal line, and then take my green one off. Yeah. You can draw a horizontal line. I'm sure we could play around with this with even better ways to find the inflection point. No. It's pretty intuitive. And there's lots of stuff online too. So I'm sure if we went to Google right now and say, how do I find an inflection point nicely on Desmos, someone will have already posted that. Very, very powerful, a very powerful app. I wonder if I can go plus minus. No. Anyways. Which is going to be nice because our next question is one that we're not as good at graphing. We're going to go out and branch out into some e to the x and cos x graphs and see what they look like. And it's going to be nice when we're unsure to be able to go to Desmos and say, was I doing this right? And this is a huge advantage that we have with our technology now, as opposed to students that were taking calculus 20 years ago. They would just be like, I hope so, right? And we can actually check out and find out, no. I don't know if that makes us in a better spot or not, right? 20 years ago, students had hope. Now they just know they're doing it wrong. Okay, so what does this look like? We've got our function. We go to preliminaries, and preliminaries, we find our y-intercept by plugging in 0 for x. And you're going to have to remind yourself of some of your exponent laws and also a little bit of your pi plate. If you plug in 0 for x, e to the 0, anything to the 0 is 1. So there's an exponent law that you need to know that an exponent to the 0 is equal to 1. And cos of 0 from your unit circle, cos is your x coordinate. Your x coordinate at 0 will also be 1. So we have a y-intercept at 1, 1. Secondly, for x-intercepts, we would set y equal to 0. And technically, you can think of this as having two factors, an e to the negative x and a cos of x. And one of the things that I'm going to expect from you for e to the negative x is to remember your graphs. And I'm going to just draw a quick graph of e to the negative x. That negative is with the x, makes it a horizontal reflection over the y-axis. And an e to the negative x graph then would look like this. We already talked about the fact when you plug in 0, you got 0, comma 1. Your e to the negative x graph looks like this. It has an asymptote at y equals 0. You can also imagine e to the negative x really as 1 over an e to the x. And I hope you realize as you plug in larger and larger values of x, if we took the limit as x goes to infinity, the bottom would become very, very big and it would approach 0. I'd also like you to notice that no matter what value of x you plug into this, it's always positive. So 2 notes from this. From this graph, I can tell it's always positive, which is going to come up later, and never 0. The fact that it's never 0 is going to help us in finding our x-intercepts, because if it's factored, this side is not possible. And then we have to think of our pi plate and say, is cos x ever equal to 0? Yes. Where is it equal to 0? Where is your x-coordinate equal to 0? Up here at the top. So we would have pi over 2 here at the bottom, 3 pi over 2. And then it would keep going forever. So you would have sort of a general solution. You could go plus 2k pi. But because our graph says only to graph up to 5 pi over 2, we'd also have to include 5 pi over 2. So those are our x-intercepts. We could list them as pi over 2 comma 0, 3 pi over 2 comma 0, and 5 pi over 2 comma 0. So there's preliminaries. Does this graph have any asymptotes? That's a good question. Does it have any non-permissible values? No, right? You're never, since this is never 0, you're never dividing by 0. We could possibly have dividing, okay? We don't. Does it have an asymptote? Most likely, because as x gets really, really big, you would have an asymptote at 0, a horizontal one, but we're only graphing between 0 and 5 pi over 2, so we probably won't have an asymptote. But we'll write it down. Because cos of x goes between 1 and negative 1 over and over again, but that 1 over e to the x will eventually become really, really close to 0. You will find your cos graph then starts to really get closer and closer to 0. But it's kind of weird because there will be an infinite amount of x-intercepts as well. We'll look at Desmos after. There's some fascinating stuff that's going to go on with this graph. But we're only graphing it between 0 and 5 pi over 2. So the exact values of the x-intercepts, we've done that. The coordinates of the first 2 stationary points and sketch, we're going to do that. So in the same manner. Hey,
sorry to interrupt.
No problem.
Are you running the second row?
I'm going to be there the whole time.
The whole time?
Yeah.
Okay.
So
Ryan and I are going to be doing the scores.
Okay.
Ty asked us to do the first one.
Okay.
And then we're trying to get a hold of St. Mary's so they can do the second and then the third one on their own.
Okay.
So we're just seeing like who's going to be doing the second one because we don't want to
I'm there the whole time. So worst case scenario.
Okay.
Yeah, that can be it. Yeah.
Okay. Sounds good.
Okay.
All right.
Perfect. Thank you. You guys are photocopying the things out?
Yeah, we have everything ready to go. We just wanted to make sure we have like people in place for that. So.
Perfect.
Okay, thank you.
Okay, so go to green, find our derivative. A little bit more challenging a derivative than the last one because we have a product rule, chain rule, some of the stuff that you've remembered and forgotten maybe a little bit. So product rule says keep one the same, multiply by the derivative of the second one. Do you remember the derivative of sine? I mean cos? It'll be negative sine plus, keep the second one the same, multiply by the derivative of the first one, and the derivative of e to the x stays the same, but this is a chain rule in where you would have to then also multiply by -1. Now we have to make our derivative equal to 0 to find the stationary points. And to solve this, we're going to factor it. Notice that you can factor out a negative and an e to the negative x out. That would leave you with positive sine x plus cos x. And again, now that it's factored, the first part, it's important that we did that graph at the beginning to say this section's not possible. That's never equal to 0. So knowing that an e to the x graph is never 0 is going to be important here. For this part, we are really trying, when is this 0, is really when sine x equals negative cos x. And there's a couple of ways that you can solve this. One, you could think of your pie plate, and you could say, when is the x coordinate and the y coordinate the same, but one is positive and one is negative? So you could think about root 2 over 2, negative root 2 over 2, or root 2 over 2, negative root 2 over 2, root 2 over 2. So those two. The other thing you can do with this, which a lot of students like, is if you divide both sides by cos, you get sine x over cos x equals -1, which is the same as saying tan x equals -1, which would give you the same pi over 4 family in quadrant 2 and quadrant 4. Now we need to solve from 0 to 5 pi over 2. That's once around the circle and then an extra quadrant 1 after that. So thinking that way, that would mean that we only have an answer in quadrant 2. So x would equal 3 pi over 4, and in quadrant 4, 7 pi over 4. So 3 pi over 4 in quadrant 2, 7 pi over 4 in quadrant 4. Now, finding those values, definitely a calculator question. In fact, I'm going to leave them for Desmos. Those are going to be our 2 points, but to find out about them, and on my number line this time for my derivative, I'm also going to add 0 and 5 pi over 2 because those are endpoints. There would be more places where tan is equal to -1 if we extended. So if we didn't put our endpoints on here, you might have said, oh, what's less than 3 over 4? -100. And I'll try it, but I won't necessarily be in the right spot then. Okay? For sure, I can try something between 3 pi over 4 and 7 pi over 4. Okay? Probably pi would be a nice number to test because you can do the mental math of that easily. First of all, this part out front, I hope you can see, is always negative. Because the e to the negative x is always positive, but the negative out in front would make that section always negative. So this analysis that we did at the beginning for 1 over e to the x, to note that it's never 0 and always positive, has come into this question a fair bit already. So this section's always negative. If I plug in pi, we're going to have to think about our unit circle. Sine of pi is 0. That's your y coordinate. Cos of pi is -1. So this would be negative as well, meaning this section in between here is positive, and our graph would be increasing. If we plug in a value like pi over 4, again, this first section is always negative. Sine of pi over 4 is root 2 over 2. Cos of pi over 4 is root 2 over 2. Adding them together will be positive. So this section, negative times positive, this section will be negative. would be decreasing. And again, something above 7 pi over 4 but less than 5 pi over 2, I'd probably choose 2 pi. So choosing 2 pi, sine of 2 pi is 0. Cos of 2 pi is 1. This is positive again. Negative times a positive. It will be decreasing. So from our diagram, we now know that this is a minimum and this is a maximum. And as far as this question goes, it says the coordinates of the first two stationary points, and then it says sketch the graph. So if we wanted to be really accurate, we could do the second derivative right now. What we're going to do is we're going to just take the information that we know and see how good our graph could be without our calculator. Then we're going to use Desmos to double check things. So what do we have so far? We have between 0 and I'm going to just mark 5 pi over 2 on there. Those are our points. We have a y-intercept at 0, 1. And our x-intercepts are at pi over 2, 3 pi over 2, and 5 pi over 2. Pi over 2, pi, 3 pi over 2, 2 pi. Pi over 2, 3 pi over 2, and 5 pi over 2 were all x-intercepts. And we know that we have a maximum and a minimum at 7 pi over 4 and pi over 4. So we could, without a graphing calculator, just a scientific calculator, you could plug in 3 pi over 4. I'm going to mark on my pi plate here, 3 pi over 4 would be right there. 7 pi over 4 would be right there. And we know that 3 pi over 4 is going to be a minimum. I don't know exactly where this point is. I'm going to just imagine some minimum, imagine some maximum, and our graph is going to look like this. More or less. We don't know how high or how low those maximums and minimums are because we didn't take the time to plug them in. We definitely could have done that. Now going to Desmos. Can easily push the x's to erase graphs. We want e to the exponent of negative x bracket cos x. And what we're concerned about was between 0 and 5 pi over 2. Wow. There's probably a way I can change my scale even. I've got to get even better at Desmos. I bet you I could make my scale on Desmos go by pi over 2s. Hit the tool button. Yes. Oh, we can set it from negative 0.1 up to 5 pi. It's intuitive. I like that. Oh, and we can do our steps. There's where I was looking for. Pi divided by 2. Nice. Now, there's our minimum. So I'm going to click on this graph. There's the minimum. That's at 3 pi over 4 comma negative 0.067. So our graph was a little bit exaggerated. And here's our maximum, fascinating enough. It's at 0.003. So it's very, very close to 0. We do have our point at 0, 1 that we found and our x-intercepts. So Desmos, great, okay, because I'm going to unclick it so you don't see the points. But with your eye, can you tell that there's a maximum right here? Or does it just look like it's going to a straight line? As soon as I click on the graph, it automatically figures out that maximum. In fact, if we zoom out, there's a maximum there, then there's a maximum there, then another one there. Like, it just looks like a straight line in the end. In fact, we zoom out over and over and over again. And you know how I talked about there should be an asymptote at 0? There technically is, but the graph is doing like a squiggle closer and closer to 0, so it eventually is almost a straight line, but it does continually have x-intercepts on there. If I click on the graph now that I'm zoomed out, look at how many maxes and mins it's found and x-intercepts in there. And it knows, and it figures them out as we go along. And then it starts to get to be huge after that. Fascinating. Okay. All right, so that is Desmos for that one. What did we say our values were? 0.03 and negative 0.067. So we can go back to our graph and add some accuracies. And then we realized that our graph wasn't very much to scale. But again, the power of Desmos over your graphing calculator there is that it automatically finds those max and minimums. You just have to click on them. You're going to have to play around with your graphing calculator quite a bit to see that window. So highly recommend that you download that Desmos app just for how powerful it is. Okay. I want you to do this one on your own with the preliminaries. So if we think color coding, we did the black section preliminaries, then the green section with your first derivative to find your stationary points. Then you don't have purple. The purple section where you did your second derivative to find your inflection points. Then you can show where it's concave up and concave down. So check how you did. First of all, the green part, you found your derivative, set your derivative equal to 0, have your number line for your derivative, and then found out that your local max and your local min were those points. Next, the purple section. Sorry, I changed the shade of purple. I like that. You should do that. Just change the shades every day to keep it fresh. So our inflection point, 1, negative 31. And now putting that all together, this is what your graph would look like. And I'll put up the answer for the last one. It says, show that it doesn't have an inflection point. So imagine that in green. Imagine that in purple. And a little explanation. So if you found your first derivative, you'd find out that 0, 0 is a local minimum. And when you find your second derivative, even though it's equal to 0 at 0, it's concave up before and concave up after. So it doesn't follow the two things to be an inflection point. An inflection point only happens when the second derivative is equal to 0 and it changes concavity.